Hey everybody, happy Wednesday. We are both really excited and a little bit terrified to be shipping out our beta tester kits this week. We're really excited because I can't wait to see all the amazing things you guys are going to build and all the improvements that you guys are going to make both to the mechanical design of the machine and to the software. It's a little bit scary too, just because it's always scary to share something that you've built. I think it's even maybe a little bit more scary to share something that you're in the process of building. So just personally, that's a little scary. This week what I want to talk about in this video is how we're all going to collaborate together and what to do when things go wrong. I'm sure things are going to go wrong. It's kind of how launching hardware is. But we want to be organized and have a system in place for how you can make improvements and suggest changes, how you can report something that's wrong, and how we can all share knowledge and collaborate and work together.
The way we're all going to coordinate is through this website called GitHub. And GitHub is basically a platform designed to allow people to work together on both open source projects and in big companies. But it's free for open source projects because they're trying to support the open source community, which is fantastic. If you haven't already made an account with them, I highly recommend it. So this is our GitHub page. And you can see it's split into different sections for the firmware, for ground control, for the mechanics of the machine, and for the electronics. So let's say we find something wrong with ground control. So we'll go in here into ground control. And there's a couple things we can do. The best case scenario is if you find something wrong and you know how to fix it, and you can fix it, is to fix it and create what's called a pull request. And so a pull request is basically saying, hey, here's something that I've fixed that I'd like to be merged back into the main piece of software. So we don't have any open right now, but if we click here on the closed pull requests, we can see things that have been added in the past. So basically what this is an idea for improving the software that was added. And each one has a place where we can talk about what's changed and discuss how that's going to improve the software. So those are pull requests. If you find something that's wrong and you're not quite sure how to fix it, or you just don't have time to fix it, you can create what's called an issue. An issue can be either something that's wrong, or it can be something you'd like to add that you think would make the machine better. And so these are all issues. And each of these issues has a place that we can discuss what's wrong. So basically, there's a conversation that can go on about how to fix it. And that's really helpful. That creates a place where we can all work together. And finally, if you find something that's not necessarily wrong, but you find a piece of information you'd like to share with the community, that can be shared through the wiki. And the wiki page is basically a place for all of our collected information to be stored and not lost.
Using this system is going to be really important because starting next week, you guys are going to outnumber me 100 to 1, and in a couple months, you're going to outnumber me closer to 1,000 to 1, which basically means the community is going to be making improvements to the software, to the hardware, and generating knowledge about how to best use this machine much more quickly than I ever could working alone. And that's awesome. That's why we're open source. That's why we have this focus on working together, creating a collaborative community. It also means that it's really important that we have a good system in place for everyone to collaborate so we can all work together efficiently. To get us started on that process of working together, I want to talk about two of the biggest issues that I think are still with the machine. The first has to do with the sled. Early versions that we showed up until we started showing this round sled a couple weeks ago use basically this plate that comes with the router to slide along the wood. This works pretty well. It's designed to do this. It's kind of a hard plastic. It's pretty low friction. It had a couple drawbacks. One, this comes with your router, so it's going to be different for each of our routers. And I don't really like that because we want it to work with kind of any kind of router. The other big drawback to this is it's pretty small and it has pretty sharp edges, which means as it's sliding along, it has a tendency to get caught in things that have already been cut. This much bigger plate is better in many ways. First of all, you cut it out with the machine itself, so we can all improve on it and have the same one. it's much, much stabler because it's much bigger. The drawback is it has much more friction, which means as you're cutting, especially down in the bottom left and right corners and all the way over here at the edge, this chain has less tension than I'd like. This chain being tensioned ensures everything stays accurate. If it has a little bit of slop in it, basically the friction between this and the wood is causing this chain to be too slack. So what I'm thinking a solution to that is to actually pocket out a lot of this space. So there's not a lot of surface area. Basically, there's just going to be a ring around the edge in contact with the wood. I'd like to hook the dust collector up to that space that's created. I think we can actually get better dust collection that way. But I mean, I haven't tried it yet. I'm going to be probably pretty busy for the next week or two, so I probably won't have a chance to try it. So I think that's the first big thing that I'd like to change about the hardware. The next thing I'd like to change is about the software. It has to do with the way the motors are calibrated, and it's going to be easier for me to explain if I just show you some data. So before we talk about motor calibration, let's talk about why motor calibration is important in the first place. So let's look at the firmware architecture as it is right now. So at the top here, it's this sort of object-oriented hierarchy. At the top, we have the CNC router. It takes a line of G code. It turns that into motion in the 3 axes. Each of these axes is a closed-loop controller, so it's continuously reading its position and correcting by commanding a speed at the motor. And what we notice here is there's a little bit of a disconnect where this controller is commanding a speed while the motor is really receiving a voltage. And so for that to work, we assume that there's a direct relationship between the applied voltage and the speed at which the motor rotates. And so when we look at the data, what we'd like to see is this nice straight blue line here. When we look at the actual response of the motor, it's this curve. So to correct for that, we do calibration. And basically, calibration measures this curve. The machine automatically measures this curve and corrects for it. And that works really, really well right where you've done the calibration. The problem is that as you move across your 4x8 area, the tension in the chains and the torque experienced by the motor changes, and so you get a different response curve in different places. And I started to go down the road of calibrating in multiple places and then doing some fancy math to figure out what calibration to use. That turned out to be way too complicated. I think it leaves too many options for things to go wrong. And there's a way I'd like to do it, which I think is much simpler and is going to give us much better results. And that is to change the firmware architecture to look like this. So at the top here, everything's exactly the same. We have our CNC router. It's reading a line of G code. It's commanding positions for the axes. Each axis is still a closed-loop controller based on position. And what's different is we've added this extra module in here. And so this closed-loop controller is based on position. It's commanding a speed. This is a second closed-loop controller, but instead of being based on position, this one is based on speed. So it's continuously measuring the motor's speed and applying a voltage to correct it. And what this one does is this module will correct for any changes in torque experienced by the motor. And so say, for example, you were cutting something and you set an extra brick on top of your sled. This module here will compensate for that, and your positional controller up here will be unaffected. And so I think that that's going to be, there will be no calibration involved. It's all automatic. And I think that that's just a better way to do it. And that's something I'd like to add as soon as possible. Thank you for watching, everyone. We can't wait to see you guys start building some amazing things.